Hope you all are safe. Stay home, stay safe. So we stop with the chapter sampling. After that you have two more chapters, optimization and calculus of variation. So today I will be covering the chapter calculus of variation, and the other chapter optimization my colleague is covering. So I am not elaborating this chapter much, only from the exam point of view, whatever is needed, only those topics I will be covering. And I already sent the notes. I think by this time you all got those notes, so you go through those notes. And the reference textbook for this particular chapter, Calculus of Variation, is Higher Engineering Mathematics by B.S. Grewal. So to begin with the chapter, we need the definition of functional. So to define a functional is actually a function defined from the set of all functions to the set of real numbers. Consider a set S, where S is the set of all functions. Now, a functional is a function. Say a functional is a function from the set of all functions to the real numbers. So, a functional is a real valued function which is defined from the set of all functions. I will explain it with an example. You consider the set of all functions which is defined in an interval 0, 1. So you consider the set of all functions which is defined in an interval 0, 1. So those functions can be anything, say sin x, polynomial function, e power x, it can be anything. So now I can define a function I from this C of 0, 1 to the set of real numbers in such a way that I is integral 0, 1 y of x dx, where y of x is the set of all functions defined over 0. And this is an example for a functional. You understood? So this is an example for a functional. In calculus of variation, our main aim is to find the maxima or minima of a functional. So I'll explain with one more easier example. Consider 2 points, say A of x1, y1 and B of x2, y2. Now you can find out infinitely many curves joining these 2 points. Say curve y1 of x, curve say y2 of x, curve y3 of x, etc. Now, what is the arc length between these two curves? The arc length between these two curves is given by integral x0 to x1 root of 1 plus dy by dx the whole square dx. Now this is an example for a functional. And in calculus of variation, our aim is to find the maxima or minima of this particular functional. Or in other words, I can say my aim is to find out the curve y of x in which this arc length is minima. So Euler equation will help you in finding extrema of a functional. That means maxima or minima of a functional. So I will explain Euler's equation, but the proof is not required from the exam point of view. So those who are interested to refer the proof, you can go to Grewal. The proof is explained. You can go through that. And if you are unable to understand it, you can contact me through WhatsApp. So I am not going to explain the proof of Euler's equation. I will just give you the Euler's equation to find the extrema of a functional, and there are 2 more forms for Euler's equation. So Euler's equation will help you to find the maxima or minima of a functional. So In general, we are representing a functional by I is equal to integral x0 to x1 f of x by y dash dx. A necessary condition for the functional I is equal to integral x0 to x1 f of x y dash dx to have an extremum is given by dou f by dou y minus d by dx of dou f by dou y dash is equal to 0. So this is our Euler's equation. You have two more forms for Euler's equation. So there are two more different forms for the Euler's equation. Just by applying the properties of derivatives, you get those two more forms. So I'll just give those two more forms of Euler's equation. The second form of Euler's equation is d by dx of f minus y dash dou f by dou y dash minus dou f by dou x is equal to 0, which is the second form of the equation. And the third form of the equation is given by dou f by dou y minus dou square f by dou x dou y dash minus y dash dou square f by dou y dash minus y double dash dou square f by dou y dash square is equal to 0. These three equations I have given in the notes. I have explained these three equations in the notes which I sent already. So now using any of these three equations, you are able to get the function y equal to y of x. Now the first case is, suppose the given function f of x by y dash. Suppose the f is independent of x. So if f is independent of x, what you get? Dou f by dou x is equal to 0. So if dou f by dou x is equal to 0, you can go to the second equation. So in the second equation, if dou f by dou x is equal to 0, what you get? You get only this part. So you get d by dx f minus y dash dou f by dou y dash is equal to 0. By integrating that particular equation with respect to x, you will be getting f minus y dash dou f by dou y dash is equal to 0, which is a differential equation of first order, and you already studied the method for solving differential equation. Anyway, you don't worry, I will be explaining it while solving the problem. So by solving is equal to C1. See, by solving this equation, you are able to get the solution y equal to y of x. So that is the first case, when f is independent of x. Now the second case is when f is independent of y. So when f is independent of y, you get dou f by dou y is equal to 0. So when dou f by dou y is equal to 0, you can go to the first equation. The first equation is having the term dou f by dou y. So when dou f by dou y is equal to 0, you can rewrite the first equation of the form d by dx dou f by dou y dash is equal to 0. By integrating the equation with respect to x, you get dou f by dou y dash is equal to c1, where y dash is dy by dx. So again we are getting a differential equation of first order. Solve the differential equation to get y equal to y of x. So that is the second case. Now the third case is when f is independent of x, f is independent of y dash. So when f is independent of y dash, you have dou f by dou y dash is equal to 0. So again, which case? You can consider, go to equation 1. So when dou f by dou y dash is equal to 0, we will left with dou f by dou y is equal to 0. Solving the equation, you can get the solution for y of x. And the fourth case is when f is independent of x and y. So when f is independent of x and y, you can say dou f by dou x is equal to 0, dou f by dou y is equal to 0. Similarly, dou square f by dou x dou y dash is equal to 0, and dou square f by dou y dash is equal to 0. So we can go to the third equation. So in the third equation, these all terms dou f by dou y and these all terms are becoming 0. We left with y double dash dou square f by dou y dash square is equal to 0. Again, by solving this particular equation, we can find the solution y is equal to y of x. So in the next class, I'll explain how to solve a functional with the help of these equations. Thank you.